Hello, my name is Andrew Zulu. Welcome to this presentation on three-dimensional equilibrium. We will cover the following: a free-body diagram, categories of equilibrium, and then we will do some examples. Let's get started. So we define what is called the necessary and sufficient conditions for equilibrium, which are that the summation of forces must be zero and the summation of moments must be zero. So in the orthogonal directions x, y, and z, this can be split up into summation of forces in the x, y, and z equal to 0, and summation of moments in the x, y, and z equal to 0. So the vector approach is more suitable for equilibrium analysis in three dimensions, as we'll see later. Now let's look at free body diagrams and how we can draw them for particular situations. So for example, if we have this body here, okay, and it's a member in contact with a smooth surface or a ball supported member, then we just put the reaction force N in this case. If it is a round surface, then we put the reaction N and also the frictional force F. Okay, if it's a roller or wheel support with a lateral constraint, then we have our normal force N, and then for the lateral constraint we have to put our reaction force in this direction here. If it's a ball and socket joint, then we have to represent all three of the reactions, which is Rx, Ry, and Rz. If it is free to move, if it is fixed, then apart from the Rx, Ry, and Z, we have to represent the moments Mx, My, and Mz. Now let's look at categories for equilibrium. Okay, so before we look at categories for equilibrium, we have also a thrust bearing. So for a thrust bearing, obviously it does not take any load in this direction here. Then we have Rx, Ry, okay, and then the moments in the X and Z, and then there is no reaction here in the Y. Then for categories of equilibrium, we have concurrent at a point. The forces meet at a point O. In this case, we have F1, F2, F3, F4, and F5. They meet at a point O. Okay, then we have to say summation of forces in the X, in the Y, and the Z is equal to 0. If they are concurrent on a line, then it's the summation of forces in the X, Y, and Z equal to 0, but at the same time, we must take moments in the Y and in the Z. A moment in the X is 0, so it's not defined. In this case, it's actually 0. And then if they are parallel, we have F1, F2, and F3. Okay, we have to take summation of forces in the direction in which they are parallel. Okay, and then we must take now moments in the Y and in the Z. So in this case, the moment in the X is going to be 0, so you have to take moments in the Y and also in the Z. Then the general force representation like this, we have to take all forces in the X, Y, and Z, and the moments in the X, Y, and Z. Let's look at an example. So here is our example. It says bar ABCD of negligible weight is supported by a cable BE and bearings at A and D. So we have a bearing here and a bearing there, the latter being a thrust bearing. So BE and CD are both horizontal, so this is horizontal and this is also horizontal. Determine the reactions at the bearings A and D at the tension in the cable BE. So this is the free body diagram. So at A we represent all three, AX, AY, and AZ, but at D we do not represent in the thrust, because it's a thrust bearing, so we don't represent this load here, which is in the Y. So we represent only DX and DZ. And then we represent, of course, BE and the 250 newtons. So from the free body diagram, this free body diagram, we can say the summation of moments at A is R, is the summation of all the R cross F's of all the forces that we're looking at. So we're going to take moments at A because A has the most forces. We want to take moments at the position where you can eliminate the maximum number of forces. Okay, so the first one is going to be this one, BE. So it's in the Y direction. So as a vector to be written as BEJ. And then its moment arm is the 6 in the x direction, so we're going to call 6R. So it's 6R cross BEJ. Okay, and then we come to the 250. The moment arm is still 6R, and then the line of action is right here, and then cross minus 250K, because the 250 is going opposite to the Z, and then plus. Then we take the moment arm from A like so. So the moment arm will be 6R minus 3.6K plus 4J, and then we cross multiply with these two. So this one will be minus dxi, and this will be dzk. Okay, when we do the arithmetic, this is what we come up with. So it comes to the following. Okay, and then what we do after we've done this cross multiplication, we take all the k's together, all the j's together, and all the i's together. So taking the k's first, we have 6be, okay, plus 4dx k is equal to 0, and then from here we can be able to say that dx is minus 6 over 4be, which is minus 1.5 be. Then putting the j's together, 1500, and then we have 3.6 dx, and then 6 dz, okay, is equal to 0, like so. Then we can say 6 dz minus 3.6 dx is equal to 1500. And then put the i's, there's only one I, 4 dz is equal to 0, which means dz is 0. Then we take this 0 here, and then we solve for dx, and we find that dx is minus 417. Then we take the 417 into this equation, and then we can calculate BE, and it will be equal to 478. And then we take summation of 478x. Okay, then we're going to say ax minus dx is equal to 0. Now dx was already found to be 0, which means x is also 0. Then summation of forces in the y, which is in this direction here, we have this BE minus this AY equal to 0. So it means AY will be the same, it will be equal to BE, which is 278. And then in the Z, we have DZ plus AZ minus this 250 here is equal to 0. Okay, this has been found to be 0, so AZ is 250. So to find the action at A, what we do is we just Pythagoras AX squared plus AY squared plus AZ squared. So AX, AY, AZ, and we should find that is 374. And the forces at D is simply dx, because dy was found to be 0, which is 417 newtons. Okay, now let's look at the second example. So we have a 5-meter pole is held by 3 guide wires anchored by bolts at B, C, and D as shown in the figure. The tension in wire AB is 5 kilometers. So the tension here is 5 kilometers. Calculate the vertical force P exerted by the pole on the pin at A and the tension in cables AC and AD. So let's see how to do this. So here is the free body diagram. So we have the force in AB, force in AC, and force in AD, and then the reaction at the pole, which is P. Okay, so the first thing that we need to do is to write the unit vectors in the direction AB, AC, and AD. So let's begin with AB. So if you look at AB from A to B, in the X, we're going to be moving backward by 1 meter, this one. So we're going to say minus I. And in the Y, we're going to be moving backwards by 1.5 meters, minus 1.5 J, and in the Z, it's minus 5K, divided by the square of the Pythagoras of these 3 numbers. Okay, then we get this. AC, so from A to C, in the X, we're going to be moving 3 meters positive, 3I. In the J, we're going to be moving backward by this 1 meter, minus 1, and then in the Y is minus 5. Then we Pythagoras the 3 numbers, and this is what you get. Then the unit vector in the direction AD in the x, you're going to be moving backwards by 1 meter in this case, similar to here, backwards by 1 meter, which is -1. In the y, you're going to be moving forward 3.7 meters, 75 meters. In the z is -5. In Pythagoras, these three numbers, and you get this. So these are the unit vectors in the three directions. Now let's see how to solve the problem. Okay, so now we know that the summation of forces will be 0, okay, at any point in time in this case. Okay, then we have FAB plus FAC plus FAD plus P. So these three forces added should be equal to 0. So FAB is the unit vector that we saw before, plus FAC plus FAD plus PK. So P must be written as a vector, is equal to 0. Then the next step is to take all the i's together. So for example, the first I is FAB times -1 divided by this. That's the one. Then the next is 3 square root of 35, okay, FAC. And then the next I is -1 and that FAD. You get that? You do similarly for the J's, you group them together. Similarly for the K's, you group them together. Then you substitute the value FAB is 5 kilonewtons, that's what we were told, and then you solve for FAC, FAD, and P. How do we do that? So we take this is equal to 0, and this is what you see here, and that is equal to 0, this is what we see here, and then this is equal to 0. This is what we say, the summation of forces is 0. So this is equal to 0. Okay? So it is left to the reader to show that we have three simultaneous equations here, and the three unknowns are FAC, FAD, and P. Okay, when you solve these three simultaneous equations, you should be able to find. You can use Gauss elimination, or you can use a matrix, okay, to invert this matrix. Okay, you can do whatever you want basically. You can use Excel or MATLAB to solve. Okay, and you should be able to find that FAC is 2.85 kilonewtons, FAD is 3.2 kilonewtons, and the P is going to be 9.64 kilonewtons. That's it for this segment. In this video, we have covered three-dimensional force free body diagrams, three-dimensional categories of equilibriums, and then we have looked at some examples. Thank you for your kind attention.